Okay, here's our second set of problems. We have a two-stage speed increaser gearbox with an input speed of 85 RPM. Helical gears with a 20-degree pressure angle are used. The input stage has a gear with 70 teeth meshed with a pinion with 16 teeth. The output stage has a gear with 28 teeth meshed with a pinion with 14 teeth. The diametral pitch of the gears in both stages is 10 teeth per inch, and the power to be transmitted is 16 horsepower. So we're going to calculate the speeds of the intermediate and output shafts, the gear's pitch line velocities, and the transmitted load, the radial load, and the total force between each gear mesh. So we have N2 equals 70, N3 equals 16, N4 equals 28, and N5 equals 14. Input speed, 85 RPM. So to calculate the speed of the counter shaft, we just do 85 RPM times the teeth ratio. So we have a speed increaser. So just take 70 over 16, 371.9. And then we're just going to multiply that by 28 over 14 to get the output speed. So 743.8 RPM. So this is the speed of the counter shaft. This is the speed of the output shaft. Now let's look at pitch line velocity. I'm going to draw a side view. Gear 2, gear 3. Let's say this is the direction of the angular velocities. The pitch line velocity is the linear velocity where the two gears meet, and it's given in feet per minute. And the formula is pi d n over 12, and this is going to be feet per minute. So you can use either gear 2 or pinion 3 to calculate pitch line velocity. It's going to give you the same value, and that's important. So the pitch line velocity, again, is the same for gear 2 and pinion 3. So we're going to figure out the pitch diameter of 2 in a second. The speed is 85 RPM, 12 inches per foot. So to figure out the pitch diameter of 2, we use diametral pitch equals the number of teeth divided by d. So d equals n over p. We have 70 teeth divided by 10 teeth per inch. So 7 inches. I'm going to show you what this looks like in my analysis tool. So equation 1334 is pitch line velocity, 7 inches, 85 RPM gives us a pitch line velocity of 156 feet per minute. Let's do gears 3, or rather 4, and 5. It's going to be the same process. Let's use the pinion just for fun. So the pinion speed, pinion 5, 743.8. And the pitch diameter of 5, 14 teeth divided by 10, so that would be 1.4. So a pitch line velocity of 273 feet per minute. All right, lastly, let's look at the transmitted load, radial load, and the total force between each gear mesh. Let's look at a side view of gears 2 and 3. So if we assume angular velocities acting this way, here would be our pressure angle. And then let's draw gear 3, 2, 3. Let's draw gear 3 in more detail. So here's gear 3. So there are 3 different force components acting on gear 3. There is the total force acting on gear 3 by gear 2. So you can kind of think of it as gear 3 rotates and it kind of bumps into one of the teeth of gear 2, and gear 2 pushes back on gear 3 with this F32. So this is also called F total. And there are two components to F total. One component is called the transmitted load, so WT, transmitted load, and the other component is the radial load. So common procedure, we'll figure out what WT is first, and then using triangle geometry, we can find F total and F rad. So let's look at the formula for WT. So transmitted load is 33,000 times H over V, where H is power in horsepower, and V is pitch line velocity, which you already know is in feet per minute. So let's see what this would look like in my analysis tool. So we previously calculated the pitch line velocity to be 156 feet per minute. Equation 1335 should go in your analysis tool. So our power is 16 horsepower. The pitch line velocity is called from above, so our transmitted load is 3,390 pounds. And then just using simple geometry with the pressure angle, you can figure out F rad and F total, and I'll leave it to you to do that. And then if we looked at gears 4 and 5, pitch diameter of 5 is 1.4, the gear speed 743.8, the transmitted load 1,937 pounds, and again, F rad and F total are calculated just based on the pressure angle. Okay, so really all you need is 1334 and 1335 to answer those questions. Okay, in this next problem, we have a compound reverted gear train needed to provide a 40-to-1 plus or minus 1% increase in speed while minimizing the overall gearbox size. Assume a 20-degree pressure angle and specify the appropriate tooth numbers. So we'll just have to draw a picture of what's going on. So we have an increase in speed, so that means we're going from a larger gear to, whoops, it's a little weird, a smaller pinion or shafts. And then again, we're going to speed it up by going from a larger gear to a smaller pinion. There'd be some bearings here. All right. So our total train value is 40. And we want to keep these two stages as close to the same size as possible because that is what is going to help us minimize the overall gearbox size. So we're going to split this E total into two stages. And the easiest way to do that is just to take the square root of 40. And we can do that because we have a little bit of wiggle room in the gear ratio we need to achieve. And you'll see when this is not the case with the next examples. So square root of 40 is 6.32. So let's say our train value for stage 1 is 6.32, and our train value of stage 2 is 6.32. Remember that in any given stage, you don't want your train value to be greater than 10. And I guess more generally speaking, you don't want your gear ratio to be greater than 10. So since we had a total train value of 40, we're having to split it up into two stages. So this is also our M. And we're going to use the m's to figure out the minimum number of teeth on the pinion. And we definitely want to use the minimum value that we can because we're trying to minimize the overall gearbox size. Okay, so we have 20-degree pressure angle. We can get exact values, so square root of 40. 16 exactly. Okay, so we'll go with that. So we'll call this 2, 3, 4, 5. So we'll say N3 equals N5 equals 16 teeth. And we'll just take M1 equals 6.32, and that would be N4 over 16. So 16 times 6.32 is 101.12. So let's go with 101 teeth and see if that works, because smaller number of teeth means a smaller gear, and we're trying to minimize the gearbox size. So how do we check this? So the product of the driving teeth over the driven teeth, I should say product. So 2 and 4 are the drivers, so we'll say 101 times 101 divided by 16 times 16. Get 39.85. And is that within 40 plus or minus 1%? 1% of 40 is 0.4. So yes, this would work. So 101 teeth for N2 and N4, and 16 teeth for N3 and N5 would be the correct answer. Okay, now let's say we have to achieve an exact 40-to-1 increase in speed while minimizing the overall gearbox size. So I'm going to draw the same picture. We're adding on in complexity because now we don't have that wiggle room. So here what we're going to do is kind of interesting. We're going to take our gear ratio of 40-to-1, and we're going to split it up into two integers that are close in size to each other. So this is going to be our M, let's say we called this M1. So let's say M1 is 8 and M2 is 5. Doesn't matter, M2 could be 8 and M1 could be 5. But you want to keep these two numbers as close as you can to each other because we're trying to minimize the gearbox size. So we want to keep stage 1 and stage 2 close in size to each other. Let's go to our analysis tool and see what the minimum number of teeth of the pinion would be if we had an M of 8. 16.2, so 17 teeth. And then we'll just do 5 since we're here. 15.7, so 16 teeth. So using equation 1311 in our analysis tool, we have N5 so far 17 teeth, and N3 is 16 teeth. So in general, when the gear ratio is larger, meaning you have a larger gear meshing with a smaller pinion, you're going to have more teeth on the pinion to avoid interference. So that's what this is saying. M1 equals 8 equals the number of gear teeth over the number of pinion teeth. gives that the number of gear teeth is 8 times 17. 136. And then M2 equals 5. 5 times 16 equals 80. And then let's check. So if we do 136 teeth over 17 teeth times 80 teeth over 16 teeth, we have to get exactly 40. If I'm punching everything into my calculator correctly, that would give us exactly 40. So let's recap a little bit. We had to achieve this overall train value of 40. We can't achieve it in one stage, so we had to split it up into 2 stages. And we had to achieve it exactly. So the product of M2 and M1 had to be 40 exactly. So to do that, we split 40 into 2 integers. They have to be close in size to each other, so we minimize the gearbox size. It's fine. So this becomes M1, this is M2. We enter this into our analysis tool, equation 1311. It spits out a minimum number of teeth, which was 17. And then we put 5 into our analysis tool. That spit out a minimum number of teeth of pinion 3 of 16. And then from there, we multiplied the minimum number of teeth by the M1 and M2 values to get the number of teeth of the gears. So that's going to take a little practice, but your homework is going to step you through that. And then here is as complex as we're going to get. This is kind of interesting. So now we have to provide this exact 40-to-1 increase in speed while minimizing the overall gearbox size and keeping the input and output shafts in line. Okay. So one more constraint. So the input and output shafts in line mean that they have to literally lie on the same line. So again, this is our in, this is our out. So we're going to keep the same criteria. So we'll say M1 equals 8, M2 equals 5. But now we have this new constraint that we have to add in. So this distance plus this distance has to be the same as this distance plus this distance. That's pretty vague, so let's write that out. So we called this 2, 3, 4, and 5. So D2 over 2, that'd be the radius of gear 2, plus D3 over 2 has to equal D4 over 2 plus D5 over 2. So we're going to cancel out the 2's. D2 plus D3 equals D4 plus D5. Now we don't have the diameters, but we do have this relationship. The diametral pitch is the number of teeth over diameters. And again, we've seen this before, D equals N over P. So we could write N2 over P plus N3 over P plus N4 over P plus N5 over P. Now, the diametral pitch of 2 and 3 definitely has to be the same, and the diametral pitch of 4 and 5 definitely has to be the same, but they don't necessarily have to be the same as each other. But to simplify, let's just say that we're going to have one consistent diametral pitch. So P will be the same between the 2 stages. So then we can just cancel, cancel, cancel. So what we really get, N2 plus N3 equals N4 plus N5. This should have been an equal sign. Okay. So we have, let's see, we'll call this equation 1. The other equation we have has to do with the gear ratios. So M1 equals 8. So that's going to be N4 over N5. So we'll call that equation 2. And then our third equation, M2 equals 5, is MN 2 over n3. Call that 3. So we have 3 equations, but we have 4 unknowns because we don't know any of the teeth numbers. So we're going to have to come up with one more equation. And we're going to do that by specifying the minimum number of teeth of the pinion in the limiting stage. So the way to think about the limiting stage is whichever stage has the higher gear ratio. So in this case, it's this M1 equals 8 stage. So we want to make the pinion as small as possible here because we have this higher M to achieve. So number of gear teeth over number of pinion teeth. So if we make the number of pinion teeth as small as we can, it's going to allow us to make the number of gear teeth as small as we can. So that's a limiting case as compared to M equals 5. So let's enter, actually we already did this, we don't have to do this again. We entered, what did we get when we entered M equals 8? It was up here somewhere. 17, so we don't need to do that again. So this gave us NP equals 17 teeth, so we're going to use that. We did this before. 8 times 17 would give us N4, 136. Okay, so now we have N2 plus N3 equals 136 plus 17. So N2 plus N3 equals 153. And now let's use equation 3. And we can say that 5N3 equals N2. So 5N3 plus N3 equals 153. So 6N3 equals 150. Too many 3s and too many 6s going around in my head. I did it again. Hello. Okay. So let's hope the 153 divided by 6 is an integer. Dang, it's not. Shoot, we can't have that. We can't have a gear with a non-integer value. So what we can do is just try again. So we'll say, let's say N5, instead of having 17 teeth, let's bump it up to 18 teeth and see how that changes things. So now N4 equals 8 times 18 equals 144. And we'll write N2 plus N3 again equals 144 plus 18. N2 plus N3 equals 162. N2 is 5 N3 plus N3 equals 162. 6 N3 equals 162. Now let's hope that 162 divided by 6 is an integer. And it is. It's 27. Good. So we only had to do one iteration there. So we got N5 equals 18. N4 is 144. N3 equals 27. Oh, and we need to do N2. So N2 would be 5 times 27. So 135. So let's see if this is going to give us the exact 40-to-1 increase in speed. We know it meets the shaft inline and outline requirement already. So 144 over 18 times 135 over 27 equals 40. Okay, so I didn't make any arithmetic mistakes. Looks good. So this should be all that you need to complete homework 1. Thanks for watching.